Hello, everyone. Here is our presentation on reinforcement learning by Anthony Tran, Brad Lance, Connor Radkov, Nick Myers, Daniel Aycock, Haonan Liu, and Wyatt Greenlees. So, what is reinforcement learning? Reinforcement learning is a type of machine learning where a system learns how to make decisions through trial and error. Instead of being given the correct answers, it learns by interacting with an environment and receiving feedback based on its own actions. The easiest way to understand this is through the idea of a carrot and stick approach, which is what the picture is depicting there. When the system takes a good action, it receives a reward, which encourages it to repeat that behavior again. When it takes a bad action, it either gets no reward or possibly a penalty, which helps to discourage that behavior. Over time, the system starts to recognize patterns. It begins to understand which actions lead to better outcomes and which ones don't. So instead of memorizing answers, it's constantly adjusting its behavior based on experience. This is actually very similar to how humans learn in real life. We try things, see what works, and then improve over time. Now, here's an example of how reinforcement learning works. To really understand how it works, we try to think of a real world example, and it's common to think of training a puppy. Imagine you're trying to teach a puppy to sit. At first, the puppy doesn't understand what sit means at all. So it tries different actions, like maybe jumping, walking around, just stand there, go in a circle, whatever it may be. Eventually, by chance, it'll sit down. When that happens, you give it a treat. That treat acts as a reward. The puppy doesn't sit, it doesn't get a reward. Over time, the puppy starts to make the connection that sitting leads to a positive outcome, and it begins to choose that action more often. This is the exact same process used in reinforcement learning. There are a few key parts happening here. The action is what the puppy does. The state is the situation it's in, and then the reward is the feedback it receives. The system goes through the cycle over and over again, takes an action, observes the result, receives the feedback, and then updates its behavior. And the important part is that improvement doesn't happen instantly. It happens gradually through repeated experience. Now, reinforcement learning versus supervised learning, I think it's important to understand how these two compare to each other. In supervised learning, the system is given the correct answers ahead of time. For example, if you're training a model to recognize images of cats, you give it a data set where each image is already labeled as cat or not cat. So the model's job is basically to learn the pattern between the input and the correct output. This is similar to learning in a classroom, where a teacher gives you the correct answers and you learn from them. Reinforcement learning works very differently. In reinforcement learning, there is no labeled answers given. The system has to figure out what works on its own. It explores different actions, sometimes making mistakes, and uses rewards to guide itself towards better decisions. Because of this, reinforcement learning is often more challenging since the system has to balance trying new things with sticking to what it already knows works. So the simplest way to think about the difference is supervised learning is learning by being told, while reinforcement learning is learning by doing and discovering the answer. When you actually watch reinforcement learning in action, like in a simulation where a stick figure is learning to walk, the process becomes very clear, and I feel like it helps overall understanding. At the beginning, the system has no knowledge at all, so it makes completely random movements. The figure might fall over immediately or move in weird, awkward ways that doesn't look like walking. Most of these early attempts fail, which means they don't produce rewards. But occasionally, the system does something slightly better, like staying balanced for a little longer or moving forward a tiny, small amount. When that happens, it receives a reward. Then it starts to favor those better actions and try similar movements again. Over many repetitions, these small improvements build on each other. What starts as random movement slowly becomes more controlled, and eventually the system learns a smooth and stable way to walk. So, what looks like intelligence is really the result of thousands of small adjustments guided by rewards. This shows the power of reinforcement learning. It doesn't need to be told exactly what to do, it can figure it out through that repeated experience we talked about. So, overall, reinforcement learning is about learning from experience, using trial and error, feedback, and repetition to discover the best actions over time.
So, the first thing that I wanted to touch on in this section is that reinforcement learning has a lot of roots in psychology, specifically behavioral psychology. The main focus here is that agents in reinforcement learning, they learn from both rewards and punishment. And this learn happens through trial and error. When an agent does something good, it gets a reward. But when it doesn't complete the goal that it's assigned to, it receives a punishment. And this trial and error process is how they learn. But this is not really a new idea. It was formalized long before computers, like I said, in psychology. First of all, we have Pavlov and Skinner. Ivan Pavlov was a Russian scientist who taught dogs to associate the sound of a bell ringing with food. And eventually, these animals, these dogs, they would start salivating when they heard the bell, even if there wasn't food present, just because they knew that when the bell was rung, they were likely to get food. And this is a good example of learning through association. B.F. Skinner, he had his famous Skinner boxes, which were experiments with rats and pigeons. Now, these rats and pigeons, when they were in the box, they would have the choice to hit different buttons. Certain buttons would give them food, and certain buttons would shock them instead. And after lots of trial and error, the animals only hit the buttons that gave them food, and they learned not to hit the buttons that would give them a shock or a punishment. And this is kind of similar to how reinforcement learning agents work in the real world. So, one of the first reinforcement learning systems was actually created by Arthur Samuel in the 1950s. He built a program that would play checkers, and this reinforcement learning program improved by playing against itself. In this case, the reward would be winning a game or making a good move, and the punishment would be losing the game. And the program was rewarded for winning the game. And the key idea here was that the machines can actually learn from experience. This was very revolutionary because it shows that you could train a machine the same way that Ivan Pavlov trained his dogs to salivate. And like I said, this is one of the first examples of machine learning and reinforcement learning in the real world. So, one of the core problems in reinforcement learning is the idea of exploration or exploitation. So, exploitation is choosing the best option that you already know works. This would be the agent being assigned a problem and it has one or one solution in its database, and it just chooses that solution every time. On the other hand, exploration, that's trying something new. Maybe you find a better route, maybe you find a worse route, or maybe you don't even find a solution when you're exploring. And a good everyday example of this is saying that you want to go out for dinner one night. You can either go to your current favorite restaurant, which you know is going to be pretty good, or you could try a new restaurant, which could be a lot better, a lot worse, or basically inedible. And finding the balance between exploration and exploitation is really crucial in reinforcement learning because you want your agent to find better paths if they're out there, but you don't want it exploring for so long that it takes forever for you to solve the problem that you assign it. So, a good example of this is the multi-armed bandit problem. So, if you want to imagine you're at a casino and there's multiple slot machines, you don't know the payout for each slot machine, and your goal is to maximize how much money you're going to win. And this forces kind of a difficult trade-off for you. You can either stay put and keep playing the machine that you're currently playing that has the best known payout out of all of the machines you've tested, or you can walk around and test other machines for their payouts. You could go sit at a machine and it turns out that it has a terrible payout and you don't win anything. Or if you're lucky, you could go find a machine that has a much better payout than your current machine. And this is the foundation for many real-world reinforcement learning problems, because your agent faces the hard trade-off of either staying and exploiting the current route that it knows very well and it knows works, or exploring the environment and seeing if there's a better way to solve the goal that it was assigned.
So let me talk about why games are such a good environment for reinforcement learning. First, games provide a controlled and structured environment for AI system. Unlike the real world, games have clearly defined rules and boundaries, which make them easier for AI to interact with and learn from. Another important feature is that games have clearly rules and possible actions. At any point in the game, AI knows exactly what moves are allowed and what are not allowed, which simplifies the decision-making process. Games also provide clear reward signals. For example, the AI can receive rewards for winning or scoring. Uh, also, there are penalties for losing. These signals help guide the learning process. Another advantage is speed. AI system can simulate and play millions of games in a very short time, allowing them to explore more different strategies. Finally, a reinforcement learning system can train through self-play by playing against themselves rapidly. They gradually improve and discover stronger strategies. Because of these advantages, games became one of the earliest and most successful testing environments for reinforcement learning. One of the most famous example of reinforcement learning is in games is called AlphaGo. AlphaGo was developed by DeepMind, a research company owned by Google. The system combines deep learning with reinforcement learning to learn how to play ancient board game Go, a kind of chess in East Asia. Go is considered one of the most complex board game ever created. In fact, the number of possible board position is larger than the number of atoms in the observable universe. Because of the complexity, many experts believe that computers would not be able to defeat professional Go players for many years. However, in 2016, AlphaGo played a five-game match against Lee Sedol, who was one of the best Go players in the world at that time. The match took place in Seoul and attracted global attention, while AlphaGo eventually won the match 4 games to 1, which was a historical milestone in AI area. One particularly famous moment happened during the game 2 in the match was known as Move 37, which is here. Uh, AlphaGo made a move that surprised professional players and commenters because it was very unusual according to traditional Go strategy. At first, many people thought it was a mistake, but after time later, analysis showed that it was actually a brilliant move, and uh, that move actually helped AlphaGo win the game. So this moment demonstrated that AI could discover new and creative strategies that humans may never considered before. Now let's take a look at how reinforcement learning works in practice. One of the key ideas behind reinforcement learning is trial and error learning. Instead of being directly taught the best strategy, AI learns by rapidly trying different actions and observing the result. For example, when AI learns to play a game, it may start by making random moves. Many of these moves will fail at first, but the system receives feedback based on whether it wins or loses. Over the time, AI plays thousands or millions of games. Through the process, it gradually learns which action lead to better outcome. If we watch some videos of AI playing games like Mario or Go, we often see many early mistakes, but as training continually, the AI slowly develops more effective strategies, and such process clearly shows how reinforcement learning allows machines to learn complex tasks and get experience from those tasks.
Hi, my name's Daniel, and I'll be presenting on reinforcement learning in the physical world. So first of all, the goal here, moving to the physical world, is from moving from software to hardware. So moving from brain to body is kind of the analogy, um, which allows us to create robots that can adapt to unpredictable environments, not so perfect, like in software. So some of the challenges are that in software, mistakes cost points, like in a game. Um, Maybe they'll cost money if it's a larger scale software that people are using in everyday lives, but largely there's a little less harm done. Whereas in hardware, there are real stakes. Robots can cost a lot of money if they break, hundreds of thousands of dollars. And then if they break components that they're working on, they can cost a lot more, as well as possible injuries to people. So I have some photos here of some robots that use reinforcement learning. So over here we have some pick and place robots being trained. Here's Boston Dynamics Spot robot dog, which is really cool. Seen a couple of those in person. And then over here we have Atlas, another Boston Dynamics robot. It's supposed to be more humanoid. So then we move on to the learning process, which is trial and error. So to do reinforcement learning, we have a reward function. With this reward function, how are we supposed to know if the robot did a good job or a bad job? One example could be +1 point for touching the correct object in terms of pick and place, like shown in this photo. And then maybe +10 points, so more than just touching, +10 points for picking up the correct object. And then you could continue on +20 points for correctly placing the correct object in the correct container. So eventually, using this reward function, the robot will start out with a sort of random beginning. It looks very random. It's exploring the entire space of options it has, and then it will eventually stumble upon a reward, like touching the correct object, and then it will be able to optimize for that reward and then further rewards until it finally learns. So that's kind of what you'd call the aha moment. So eventually, the algorithm begins to favor actions that lead to success. So in this case, the robot figures out what actions give it more points, and so it can pick and place the correct object in the correct bin after a lot of training. Then we have simulation to reality. So the digital playground is kind of one way to think about it. So we use simulations when training robots because it is faster, safer, cheaper, and more accessible. Think about collaboration. If a bunch of engineers on one team are working on the same robot, training it is much easier if they can just all use the same simulation online and they don't have to make sure they all have the same hardware, which can get really expensive, and you have to make sure it's all identical. It also allows simulating thousands of generations or even more than that very rapidly. So you kind of get this evolution where it learns really quickly rather than training in real life. One of the challenges with this is the reality gap. So, gravity, friction, other physical aspects, they're never going to be perfect replicas in the simulation compared to real life. So, that's something to keep in mind. You'll optimize for certain things that end up just not being the way that they are in the simulation. So, one solution to this is domain randomization. That means you basically intentionally make the simulation random, messy, imperfect, so that the robot is prepared for these imperfections in the real world. So you train on that messy simulation so that it's ready for anything in the real world, basically. Next, another challenge with reinforcement learning in robotics is dexterous manipulation. So the challenge with the hand. So let's say the goal is to replicate the dexterity of a human hand so you can grasp and manipulate a lot of objects. Human hands are obviously very capable of manipulating a ton of objects. It's kind of how we got where we are today. So the ideal gripper might look something like a human hand, but that's really hard to do because, as you can see here, human hands have 27 bones, 34 muscles. That ends up being 27 degrees of freedom total. That's a lot. I've done a lot of mechanical engineering problems that have much less degrees of freedom than that, and 27 is a lot. Um, so that's really hard to program as like a robot. So the solution to this is reinforcement learning. You let the hand kind of figure out on its own how to grip things. You just let it do a bunch of simulations until it figures out, has that aha moment of how to pick up things and manipulate them. One really cool example is OpenAI, the team behind ChatGPT, everyone knows. They actually trained this robot hand you see over here on the right. They trained it to solve a Rubik's Cube one-handed using reinforcement learning. So that's real over there. Pretty awesome. So next, a lot of people are familiar with this, autonomous vehicles and navigation. So um, I would say everyone here has probably driven on the road. If you've driven on the road with some sort of autonomous driving, whether it's full self-driving or just some. So the goal here is to learn to drive safely through chaotic, unpredictable traffic, and the reward would be staying in lanes, maintaining speed, choosing optimal routes, and then obviously, most importantly, is not crashing. So it's interesting here because there's perception, which is sensing the world. You use LiDAR, which is like depth sensors, and then cameras, GPS, speedometer, and then you have the actions, which is turning the steering wheel, adjusting the pedal, using touch signals like that. But all of this perception and action has to be in one continuous loop. But then you collect that data from the perception and the action and the outcome, and you can use that data for improvement. So that's what Tesla has been doing for a long time, and that's why they have some of the best self-driving. Down here, you can see Waymo self-driving vehicles as well as our Grubhub robots. And then this is a view of kind of what a Tesla vehicle sees on the road. And then we have the human element. So now with reinforcement learning and new hardware developments, robots are becoming more collaborative. Some people call these collaborative robots cobots. So humans can work alongside these cobots safely without being afraid of getting injured. So these things can be deployed in anywhere that humans can work alongside them. So factories, homes, restaurants, hospitals, they're not there wide scale yet, but it's coming, and I've seen it a lot in manufacturing. Up here on the left, we see them used in manufacturing, and here in a warehouse. This is real life stuff. So they learn alongside humans how to improve when doing tasks. So then it ends up being that the robots aren't just programmed now, they're sort of coached by humans. So less need for code. Once they're already deployed, they can learn from anyone working alongside them. And so lastly, this is a project that I worked on something very similar here at Ohio State. So it's the Universal Manipulation Interface. Here you can see a video of what it looks like. It's originally from Stanford, Columbia, and the Toyota Research Institute. So the goal is learning in the wild. So instead of just simulations and clean labs, robots are able to learn in the wild using just a set of handheld grippers and GoPros. You can see that down here. They pick up objects to train the robot. So the GoPros pick up video of how the grippers move, and then that is fed into the reinforcement learning algorithm. And the goal for the robot is how the human does it. So the closer the robot is to the human video, the better reward it gets. So we use this at Ohio State in a project I did to try and replicate these results from Stanford. Really cool. It allows basically super simple training, and it can obviously replicate very complex human tasks here, like washing dishes, folding clothes, sorting objects, even throwing a ball. So yeah, that's really cool.
Hello, my name is Anthony Tran, and I will cover how does reinforcement look in your daily life. Now, you may wonder, with something such as reinforcement learning, how this might appear in your day-to-day life. Well, look no further than uh, simply your phone or your TV or your computer. I'm sure in the past, if you've seen your friend or relative social media platform on their phone or their Netflix, they seem to get a lot different recommendations or recommended posts compared to what you might see. Now, why is this the case? Well, the answer is reinforcement learning. And reinforcement learning does this through the fact that many modern recommendation systems use a form of reinforcement learning to maintain or drive engagement. Obviously, with so many different apps, social media, or just media content in general, in today's lives, a lot of these apps are competing for your attention and um, trying to get as much watch time or screen time of the app as much as possible for their benefit. And they do this through their recommendation systems. The way that these systems work is that they user behavior is going to be mainly emphasized for these platforms as learning algorithms. So whatever however you use the app, whatever you search or things like that will have a play in that in this system. And it is important to kind of carry on that fact that any interaction serves as feedback. So anything you do that might interact with the interface will send some sort of signal to their system. So to kind of visualize that last point as rewards, we can think of um, kind of the popular, any popular media app right now. So that could be your social media app like TikTok, or a media app like a music media app like Spotify, or kind of entertainment like Netflix. So how does a positive reward in these apps look like? Well, they take the form of watch time, likes, comments, whether you replay the media or not, or whether you complete the media. So these things kind of to circle back to our previous slide where we talked about the interaction. These are the types of interactions that will have a play into what types of things are going to be recommended to you in the future. But it's important to understand that there is a negative reward in these apps. And what that might look like is a short watch time, or maybe abandoning the TV show entirely, in the case of Netflix, or skipping over the media entirely. So maybe on TikTok or any social media platform you may like, just swiping through the video and not really watching it. So as we can see here, obviously to take this picture for as an example, maybe you only watch it up to here, which would signal to these reinforcement learning algorithms about the kind of videos that you tend to watch in its entirety, rather than the video where you might just abandon midway. So how does this system look in a diagram? Well, we could think of our agent as the recommendation algorithm itself. Um, so the thing that is programmed to kind of serve you content that it believes based on your behavior throughout the app, what types of things you tend to enjoy rather not enjoy. And the agent in this environment would be, or the environment for this agent would be the platform interface. So think of the kind of the look of the overall app or system that you're using, and how it is encouraging you to engage with different things. So for a state, it would actually be your user preferences. So the best example of this would be, think about Netflix and how you could have a more kid-friendly profile compared to just a general profile. So any preferences that the user might set will have a uh, a major impact in the type of content that you are likely to see on the app. And our action here will be, as stated before, will be that suggested content. What is likely to be a video that you'll see next on your Instagram or TikTok feed, rather than a different video. Whether the types of movies that you'll see first when you enter Netflix or Hulu or anything like that. Are the types of songs that you'll be most likely recommended, whether you're auto playing or whether you first launch the app in general. And lastly, our reward, as mentioned in our previous slide, your overall engagement with that content, whether you like the video, whether you comment on the video, whether you like the song, any type of feedback like that will, as mentioned before, send a sort of signal to these algorithms uh, to kind of keep recommending this content and keep showing you this content, or inversely, stop showing this content or show less likely of it.
Okay, my name is Brad Lance. I'm going to talk about part 6, reinforcement learning from human feedback, or RLHF. So reinforcement learning from human feedback adds on to the initial large language model training. And it does this by taking the model and taking the training set that it has and presenting this to humans. And then humans are going to give feedback on these results. And they're going to rank the outputs in order of best to worst, right? And so we start off with, we pre-train, right? You train your large language model on a massive amount of text. This is just our standard training, right? And then you're going to typically show humans, and this could be images, but in this case what we're talking about is text. And then humans rank this about what's good, what's better, what's best, right? And this creates an award system that the large language model learns and understands and uses to further train. So why do we need this human feedback? So large language model, as you might know, operates off of word prediction. The massive amount of parameters and training models to predict the next word that it's going to display. The problem with this is that these next word predictions are not always sensitive to human needs, to human context, and to different groups, right? So before you do the human feedback, you have very good prediction text, right? However, it can sound confident even when it's wrong or biased, and it may ignore tone, safety, or the intent of the user. After you integrate and use human feedback for the large language model to do another iteration of training and to rank its outputs, right? You provide better responses according to this human ranking. It's more attuned to the conversational tone, and it filters out biased suggestions. So it's difficult for a large language model to know what is a proper conversation, right? Humans, when they are given this feedback, go beyond checking for factual information, and they provide subjective scoring of human conversation. So before the human ranking, the LLM will output factual, but sometimes hard to understand, right? Meaning, sometimes it's inappropriate or insensitive for certain audiences, and it may ignore the tone, the safety, or the user intent. After human ranking, it's still factual, but it flows better, and it sounds more like a conversation. And it's more attuned to the user's comprehension level or culture. So for instance, a young child needs a different tone and level of intelligence, right, than what, say, an older person may need. Or it could be different cultures have different tones. And so this better situates the output to the user's context and end goal. So, for example, how do I pick a lock? If you prompted your large language model for this without human training, it might respond, "Sure, I can help with that," below our step-by-step instructions. So there's no consideration of the intent or consequences. After human feedback, it might say, "I'd recommend contacting a licensed locksmith. If you're locked out, here are some safe alternatives," right? So it redirects to safe legal options while still being informative to the user. Another example, if you prompted your large language model, "How do I win an argument on this sensitive topic?" Okay, so it might jump right in and say, "For this topic, these are the facts, these are the common errors," on and on, right? So it'd be blunt, no consideration of the person's frame of reference. But again, if you have human feedback for this training on a sensitive topic, it might come back as, "Consider the person's point of view first, and give you suggestions in proper tone to continue the argument." So it kind of slows the conversation to be more reflective of the situation. Some considerations, right? So this human feedback, right? When it for in this situation, it nudges the response towards preferred norms of human conversation. The responses are better suited for general population. The responses add to word prediction important qualities of conversational tone and human values. Human feedback can still introduce bias, right? So it's not a win all at all to fix all problems with large language models. And large language models with or without human feedback do not have human morality. So in other words, regardless of what's happening with LLMs, we have to remember that this these models, they don't have human morality. They know nothing about human morality, right? But what the human feedback adds is some patterns of recognition by the large language model to better converse with humans and judge what is to be appropriate.
Finally, on to our last part, the future of reinforcement learning and some of the ethical risks that come along with it. First, we're going to start with rewarding hacking. This is what we define as the cheat code problem we see in a lot of different reinforcement learning examples. So as we move on from the games into the real world, we encounter a unique problem called reward hacking. Think of it like a student who figures out how to get an A by hacking into the gradebook rather than actually studying for an assignment or an exam that they have to turn in. Because reinforcement learning agents learn through trial and error, they often find cheat codes that we didn't intend for them to use. If you tell a cleaning robot, for example, that its reward is to pick up dirt, it might realize that it's actually more efficient to dump out the dirt that it has already picked up and then pick it up again, because this will allow it to keep earning the reward and for its score to keep climbing, which is the ultimate goal of the reinforcement learning object. Next, this shows us that AI doesn't actually understand the goal of the task. It only understands that the reward we've programmed into it is what they're seeking to maximize. This leads us to the black box problem. So in traditional software, if something actually goes wrong, a programmer is able to look into the code and see exactly where that logic failed. You'll get an error message and you're easily able to fix it. But with reinforcement learning, logic is actually developed through millions of iterations of trial and error. This means that it's virtually impossible for a human to figure out where this mistake actually occurred. It becomes a black box where even the creators don't fully know why the agent chose a specific action at a specific millisecond. Whether it's a self-driving car or even a financial trading algorithm, we face a major challenge. How are we able to trust a system that can't even explain the own reasoning that it used to make the decisions that it did? Finally, we have to take a look at how reinforcement learning actually affects us in our day-to-day life. We use apps in social media such as TikTok and Netflix, and these applications actually use algorithms that want us to keep watching. Of course, this is how they earn more revenue through their ad revenue. But I think it's important for us to ask, is maximum watch time actually good for the user? Well, we have learned that it is not good for humans' health. And that's why some of these applications have been forced to create screen time monitors or reminders that you've been on an app for a little bit too long to tell you that maybe watching for so long isn't actually as good. This is certainly an alignment problem with what reinforcement learning teaches and what's actually good for humans. If we don't align the AI's rewards with humans' well being, we actually risk creating systems that are highly efficient, but they're actually very socially harmful. To wrap everything up, we started today talking about a simple puppy analogy, learning through treats and mistakes. We saw how those same logics moved into Pavlov's labs to mastering the game of Go, a very complicated game at that, and eventually to training the robots and language models such as ChatGPT or Gemini that we use in today's world. Reinforcement learning is perhaps the most human way that a machine is actually able to learn, and these agents will become more powerful. So, our job isn't to teach them actually how to win or how to up the reward or their score, but rather it's actually to teach them how to be helpful, safe, and aligned with the real world goals that humans have and society has as a whole. Thank you.